All right, let's talk about data. You know that feeling when you're staring at a spreadsheet and it's just so tangled and messy it gives you a headache? Well, today we're tackling that same exact problem, just on a much bigger scale. We're going to pull back the curtain on a process called normalization and see how to turn total data chaos into something clean, organized, and clear. Let's get into it.
I know. Ticking time bomb sounds a little over the top, right? But honestly, when it comes to disorganized data, it's not really that far from the truth. It's not just messy, it's actually dangerous. It creates these little hidden traps that can cause errors, lose information, and create massive headaches down the road. It's quietly waiting to mess with your most valuable asset, your information.
So take a look at this table. At first glance, it seems fine. You've got employee information, their skills, the school they went to. Seems helpful enough. But start to look a little closer. Why is Helico's school listed twice with the exact same address? That's kind of weird. And why is an employee's name tied directly to a specific skill? These are the little red flags, the dangerous secrets hiding in plain sight.
Now, these hidden problems we're spotting, they actually have a name. They're called update anomalies. And you can think of them like little landmines hidden in your data, just waiting for you to try and add, delete, or change something. Our messy little table here is guilty of all three of the big ones.
Okay, first up, the deletion trap. So imagine this. Employee 16, Lema Alumu, leaves the company. Standard stuff. You go into the database, you delete their row to remove them from the system. Poof, they're gone. But wait, what else just disappeared? We just accidentally erased our only record of the C++ skill. The entire concept of C++ is now gone from our database simply because one employee left. That's a huge critical flaw.
Next, we have the insertion puzzle. Let's say we want to add a new skill to the company's list, something like Pascal. So how do we do it? Well, with this table design, you can't. To add a skill, our table forces us to assign it to an employee. But if no one in the company has that skill yet, there's literally no way to get Pascal into the database. Our own data structure is holding us hostage.
And finally, there's the modification mess. Remember how we saw Helico's school listed twice with the same address? Okay, now what happens if that school moves? You'd have to manually hunt down every single time it's mentioned and change the address. If you miss even one of them, your data is now inconsistent. It's lying. You've got two different addresses for the same school. It's just an error waiting to happen.
So yeah, this is a mess. A real minefield. How do we fix it? Well, we fight back with a really powerful technique called normalization. Think of it as the ultimate decluttering method for your data, designed specifically to find and fix these kinds of problems before they can cause any damage. So to put it simply, normalization is just a systematic process for restructuring your database tables. The whole goal is to get rid of that nasty redundancy and make sure every piece of information has one and only one logical home. And when you do that, all those anomalies we just talked about, the deletion trap, the insertion puzzle, and the modification mess, they just disappear.
Before we can start organizing, we have to understand the invisible rules that connect all our data together. And the core fundamental principle behind all of normalization is an idea called functional dependency. Now that sounds a little academic, but it's actually a really simple idea. It's just about figuring out which pieces of data determined other pieces of data.
And this is just the perfect way to think about it. If I tell you we're having meat for dinner, you know we're probably having red wine. If I say we're having fish, you know it's going to be white wine. You see that? The dinner determines the wine. That simple, logical connection is exactly what functional dependency is all about.
And here's what it looks like formally. We write it as A with an arrow pointing to B. All this means is that the value of A uniquely determines the value of B. Every single time you see a specific value for A, you will always see the same exact value for B, just like dinner determines wine. This one concept is going to be our map for cleaning everything.
Okay, so with that idea of dependency in our toolkit, we're ready for the cleanup. Normalization is done in a few stages, which are called normal forms. We're going to walk through the first three, 1NF, 2NF, and 3NF, which honestly will solve the vast majority of problems you'll ever run into. Let's start with step 1.
First normal form, or 1NF, is the absolute ground rule. And it's super simple. It just says one single piece of information per box. That's it. No stuffing a list of things into one cell. Every value must be atomic, which just means it can't be broken down any further.
Here's a perfect example of what not to do. Look at that phone numbers column. We've got two different numbers crammed into a single cell, separated by a comma. To the database, this is just one long, meaningless string of text.
You can't search for one of those numbers, you can't sort by it. It's basically useless data.
And the fix is just so satisfyingly simple. We create a new row for each individual phone number. Now, every single cell has one and only one atomic value. Sure, the table is a little bit longer, but now it's clean, organized, and actually usable. Our table is officially in first normal form. Simple enough, right?
All right, on to step 2, second normal form or 2NF. First off, a table has to already be in 1NF to even qualify. The new rule here is all about getting rid of something called partial dependencies. This just means that every piece of information in a row has to relate to the entire unique identifier for that row, the primary key, and not just a part of it.
Check out this table. The only way to uniquely identify a row is by using both the student ID and the course ID together. That combination is our primary key. Now look at student name. Does the name Abel depend on both the student and the course? Of course not. It only depends on the student ID. That's a partial dependency. And it's a problem because we're forced to repeat the student's name for every single course they take.
The solution, once again, is to split these ideas into their own logical homes. We create one table just for students, where student ID correctly determines the student name. Then, we create a second enrollment table that simply connects a student and a course to a grade. No more partial dependencies, no more repeated names. Our data is suddenly way more efficient. And that brings us to our final step, third normal form, or 3NF. A table has to be in 2NF to get here. The last rule is that no column should depend on another column that isn't the primary key. We're hunting for transitive dependencies. You can think of it as a game of telephone in your data, where A determines B and then B determines C. We want to stop.
In this table, student ID is our primary key. The student ID determines the department ID. That's fine. But the student ID does not directly determine the department name. The department name is determined by the department ID. That's our A to B to C chain. This is a classic transitive dependency, and it's causing us to wastefully store the department name over and over again.
So we do what we do best. We give each concept its own dedicated table. We get a student table linking students to their department ID and a separate department table that links that ID to the department's full name. Now, if the computer sci department ever renames itself, we only have to change it in one single place. This is a perfectly organized 3NF structure.
Okay, whew. So we've gone through all these steps, splitting tables, following these rules. You might be thinking, that seems like a lot of work. And you're not wrong. So why does this all matter so much? What's the real payoff for all this careful organization?
The benefits are absolutely massive. We completely eliminate that redundant data, which saves space and, way more importantly, prevents errors. Our data integrity is now rock solid. And those dangerous update anomalies we started with, totally gone. The database becomes faster, much more reliable, and far, far easier to maintain and work with. It's a total win across the board.
You know, ultimately, every database tells a story. The whole process of normalization is really just about making sure that story is clear, consistent, and reliable. It's the difference between a coherent narrative and just a confusing, contradictory mess. So the question I want to leave you with is this: what kind of story is your data telling?